everyone, this is Asim Sarkar, Chemistry Honors, Mathabhanga College. So today I am going to discuss about a heterocyclic compound, pyridine. So if we substitute a carbon atom with a nitrogen atom of benzene, so it leads to the formation of pyridine. So basically pyridine is a weak base. Its pK value is at around 5.5. So why it is basic? At first we discuss this. You can see the structure of pyridine. This is the p orbitals of the ring, and this is the lone pair which is perpendicularly out of the ring. So all the p orbitals are taking part in conjugation. So it can be resonance with each other. But the lone pair cannot take part in conjugation because it is perpendicularly out of the ring. So the availability of lone pair increases. That's why it is basic. Now we'll compare this basicity with other compounds. This is pyrrole, and this is less basic than pyridine because the lone pair of nitrogen on pyrrole takes part in conjugation, but pyridine doesn't take part in conjugation. So pyridine is more basic than pyrrole. And now we come to reactions. The reaction of pyridine is two types: electrophilic substitution reaction and nucleophilic substitution reaction. So first of all, we will discuss about electrophilic substitution reaction. As you know, nitrogen is more electronegative than carbon atom, so it will attract all the electrons of the ring towards itself. So what happened? The energy of the ring will decreases. As the energy decreases, so it cannot attack electrophile. And if we discuss this with most significant theory, molecular orbital theory, we can say that as the energy of the ring decreases, so that means the energy of the HOMO decreases. As you know, in electrophilic substitution reaction, the HOMO of the pyridine ring will attack the LUMO of the electrophile. This is highest occupied molecular orbital will attack on lowest unoccupied molecular orbital. So as its energy decreases, so it cannot attack easily the LUMO of the electrophile. But if we increase the temperature of reaction, so we can so the electrophilic substitution reaction takes place. Now the question arises that at which position the electrophilic substitution will be more favorable. So at first we have to learn the numbering. Here is number 1 and this is 2, these both are 2, and this is 3 and this is 4. So first we see at C2 position. This is C2 positions. That means this is C2 position. If there is electrophilic substitution occurs, so let me see. This position should be negative and this position should be positive, and thus it will attack the electrophile. So this leads to the formation of this structure. Here is electrophile is attached, and now we get another conjugative structure, this. So there is a positive charge on nitrogen atom, and if you want to attack from 3 position, so this position should be negative and this position should be positive, so that this can attack the electrophile. And now this leads to the formation of this structure. Here is the positive charge and here is electrophile attached, and now by this more 2 conjugative structures are formed. And if you want to attack at C4 position, this is C4 position, so this position should be negative so that it can attack the electrophile, and this position should be positive. Here is, this is, you can see that the electrophile attacks at 4 position, and here we get more 2 extra conjugative structures. So here you can say, here you can see that if there is positive charge on negative electronegative atom, so it will more destabilize the structure. So here is one conjugative structure. At one conjugative structure there is positive ion on nitrogen atom, and there is a positive ion on nitrogen atom. So C2 and C4 position is less reactive towards electrophilic substitution reaction. So C3 position is more favorable. And now we'll discuss about some basic electrophilic substitution reactions. This is pyridine. If we react this with X2AlCl3, X equal to Cl or Br, so you know electrophilic substitution reaction attack happens at 3 positions. So Cl will be attached at 3 position. And this is nitrogen, HNO3 and H2SO4 with 220 degree Celsius. So NO2 group will be attached at 3 position. This is the mechanism. Here is HNO3 and here is H2SO4. It will breaks into H plus and H2SO4 minus. So HNO3, when HNO3 reacts to the H plus, this forms this OH2 plus and NO2, and this bonds comes here and NO2 plus forms. Now there is sulfonation, H2SO4 with HgSO4 and 200 degrees Celsius. So SO3H group will be attached at 3 position, and just like this CH3 CO whole to Hg and HgO CO CH3 will be attached at 3 position. So now we come to nucleophilic substitution reaction. As you know, nitrogen is more electronegative, so it will decrease the energy of the ring. So the at the same time the energy of the LUMO of the ring will decreases. So it is very easy to attack the LUMO from HOMO of the nucleophile. So nucleophilic substitution reaction is more favorable for pyridine. And now the question arises, at which position the attack will be more favorable. Here is the numbering: 1, this is 2 and 2, 3, 3, 4. At C2, this is the C2. When nucleophile attack here, this bonds comes to N, and it is there is a negative ion on nitrogen. As nitrogen is more electronegative, so it will stabilize the minus ion. And at C3 position, that means here, if we attack here, this bonds comes here as a minus. As you know, nitrogen, here is a lone pair on nitrogen atom, and here is a negative ion on this position. So there will be a repulsion between the negative ion and the lone pair. So it will destabilize the whole structure. Now we come to C4 position. This is C4 position. The nucleophile will attack at this position, and the bonds comes here, and this bonds comes on nitrogen atom. So as nitrogen is electronegative, so it will stabilize the minus ion. So you can see this is more unstable for C3 position. So the nucleophilic attack will takes place at C2 position and C4 position. We know that 2 positions and 4 position is favorable for nucleophilic attack, but which position is more favorable? If we discuss this, so we have to say this, that these positions is nearly to nitrogen atom. As nitrogen is electronegative, so it attracts the electrons towards itself. So this position is more electrophilic than 4 position. So the attack would be 2 positions, and it's favorable. Now number 2 is, if you react pyridine with RLi, so the alkyl group is added on 2 positions. And number 3, if you react this with this RLI. Here this is RLI, so it is like you can say that this is R and LI group LI is added on it. So this compound is the product. Now note, pyridine can tautomerizes with C2 and C4 position. So pyridine tautomerize with C2 and C4 position. So here you can see this. Here you can see this is pyridine, and at 2 positions a OH group is added. Now you know that pyridine can tautomerize with C2 and C4 position. So this OH group will tautomerize, and this comes O, and this hydrogens comes here. So it is NH, and there is double bond O. This is 2 position. And if we talk about 4 position, there is at 4 position there is a OH group, so it will tautomerize and becomes double bond O, and this H comes to here, and this is the product. And now we talk about the example with this point. Here you can see there is a NH2 group at 2 positions and is NO2 group at 3 positions. You know that 2 position tautomerizes with nitrogen, so the electron pair on nitrogen will not be available as it tautomerizes with nitrogen. So this and at first if you react with H2 and Ni, so this NO2 becomes NH2, and now if we attack this C2H5 COCl, so as you know that this position nitrogen lone pair will tautomerize with nitrogen here, so the lone pair of this position will not be available, so the attack is favorable from here, this NH2, and if you react with it, and the product becomes this, not from this NH2 group. The attack would be from this NH2 group. Now we do the second reaction on this point. There is the compound pyridine with a hydroxy group at 2 position. We will react this with POCl3. So we know that 2 position tautomerizes, and from here by tautomerization this structure comes, and this bonds goes there, and this bonds on oxygen atom, and after this will attack on d orbital of phosphorus atom. So from this structure comes. When it attacks the phosphorus atom, this bonds goes on oxygen atom to give a negative ion, and when it come back, a Cl minus group leaves, and after this structure forms, and the Cl minus which left from POCl3 and will attack again on this position, and the bond comes here to stabilize the nitrogen atom. And after this, to gain the aromatic condition of the ring, so this bond have to go there, and POCl2 group will leave. So the final product is this, a Cl atom on second position. Now we'll discuss about pyridine N oxide. What is pyridine N oxide? If we react any par acid, that may be MCPBA or RCO3H or H2O2, any par acid with pyridine, then pyridine N oxide forms. So here is the mechanism. Yes, pyridine, the lone pair of the pyridine and lone pair of the nitrogen attacks here oxygen atom, and this bonds goes here, this here, and this again takes the hydrogen atom, and by this structure forms, and it is called pyridine N oxide. So if you react this at first with MCPBA, so pyridine N oxide forms, and if we react this with PCl3, so Cl attack this on 2 position, because 2 position is more favorable than 4 position. As you know, nitrogen is electron withdrawing group, so it attracts the electrons toward itself, so it is, this position is more electrophilic than 4 position. So Cl will attack at 2 positions, and this forms this, and the O minus is will react with another molecule of PCl3 to form POCl3. And now we'll do nitration. So at first HNO3, if you react HNO3 with H2SO4, so we get NO2 plus. So first pyridine N oxide, this minus ion goes here, and this here, this here, and this will attack to NO2, and now this is double bond O, this bond goes here, and NO2 plus. And here is a hydrogen atom. To gain aromaticity, this comes here, sorry, this is here. Now we get this. And now if you react this with PPH3, so it will form OPPH3, and it will remove from this compound, and finally we get this NO2 group at 4 position. So this is called nitration. So now we come to the third reaction. Pyridine N oxide reacts with acidic anhydride. When it reacts with acidic anhydride, the minus ion on O atom will attract this carbon atom, and this bonds goes here, and when it returns, this OAC group leaves. This is minus OAC, and this leads to the formation of this structure, and the OAC, which is left from this group, will attack again H atom, and it will absorb the H atom, and this bonds comes here, and this will stabilizes the nitrogen atom, and this leads to the formation of this structure. And now these bonds will go here, and this will breaks here, and this go to O, and this will attack on CH2 atom again, and this leads to the formation of pyridine with CH2 OAC, and this is called 3,3 sigma tropic rearrangement. So this is enough for today. Thank you.